Welcome back. This is the first lecture in a series of lectures on current distribution in porous electrodes. We would set up the preamble and uh, look at the way we are going to develop this topic. So, in many electrochemical devices, materials plays a central part. If you look at a battery, say, a particular battery chemistry centered around a material played an important role in developing a battery. Okay, so having said so, the design of materials usually starts via understanding of molecular principles. If you want to start from real first principles, we may even have to go to quantum chemistry to understand the molecular principles. That is not the agenda for this course. We do it in a different course, what I call it is an applied quantum chemical course um, with a focus on electrochemical materials, catalysis, and separation materials. But in this course, we take a different viewpoint. Even in a material centric device, what is central is the VI characteristic. In most cases, the experiments are looking at the system in the following manner. You perturb the system and you understand the response. So in a battery, for example, you draw current from the battery, that is your perturbation, and the voltage is the response of the battery. That is what you try to measure. How do you model VI characteristic of an electrochemical device is central irrespective of the material that goes into the electrochemical device. So in this course, we would obtain the VI characteristic using a macroscopic description, using principles of continuum mechanics, continuum thermodynamics, continuum chemical kinetics, and continuum electrochemical transport phenomena. For the porous electrodes, VI characteristic, the equations that go into VI characteristic is fairly complex. We have already looked at VI characteristic for systems that are geometrically, structurally simple. When these equations are generalized to porous electrode, the equations become fairly complex, and in most cases, analytical solution is not possible. However, in a limiting case, in a one-dimensional systems with no concentration gradient, analytical solution is possible, and such a solution, even when obtained under restrictive condition, holds a lot of insight, which is useful for understanding systems wherein these conditions are not applicable. So, basis for this lecture has been provided in certain previous lectures, which are kind of prerequisite to understanding this particular lecture in detail. So the two lectures I would recommend you to listen to before we continue on this lecture are these two. This is one lecture and another lecture that has looked at related topics in a system that is uh, of lesser geometrical structural complexity. So let's move on. What is the big picture with respect to continuum description of electrochemical transport? We first connect the fluxes to current, and then we decompose the fluxes to three particular sources: fluxes due to migration, fluxes due to diffusion, and fluxes due to convection. In the absence of concentration gradient, this drops out, and a typical porous electrode, you don't have a convection. So all we need to be worried is how to model this particular source for fluxes, the migration being the source for fluxes. We also always emphasize on the electroneutrality condition, because deviating from electroneutrality involves significant energy penalty, which is usually not available in most of the regions of an electrochemical device. In a region very close to the electrode, at the electrode-electrolyte interface, electroneutrality need not be obeyed, but most parts of an electrochemical device obey electroneutrality condition. Then we have another equation. This is just a bookkeeping equation, right? So you take a control volume wherein the concentration can change with respect to time, and then you attribute these changes in concentration to fluxes that enter this control volume along different surfaces, and you may also have a generation term which is represented by this term. So all these equations have to be solved to completely understand electrochemical transport. These are coupled equations. To solve them is not easy, so we try to use different approximation to get different limiting conditions. So all these things have been dealt with in a series of lectures on electrochemical transport. So I'm not going to elaborate any further. So please look at how the full set of equations can be solved in different limiting condition. One such limiting condition is neglect concentration gradient. Sometimes you may eliminate migration using supporting electrolyte and so on. Okay, so this gives you a big picture on how do you look at electrochemical transport within the continuum approximation. So when you look at analysis of porous electrode with constant concentration, without concentration gradient, it is useful to focus on two resistances. One is what you are familiar from your high school, resistance concerned with an ohmic drop. So you have a characteristic length scale, you have a characteristic cross-sectional area, and you have conductivity. This can be applied to an ohmic conductor, electronic conductor. That is what you've seen in your high school. But in the absence of concentration gradient, even for an ionic conductor, Ohm's law is applicable. You can use this kind of a resistance. Another resistance that is important at the electrode-electrolyte interface involves resistance associated with charge transfer. Any resistance is because of an activation barrier that exists for that process. And both ohmic drop, that is ionic motion in the electrolyte, as well as charge transfer across the electrode-electrolyte interface involves activation barriers. Therefore, you may associate a resistance with that. So here again, you have a characteristic cross-sectional area. You have an over potential. This is the surface over potential. Change in surface over potential with respect to change in current is a measure of resistance associated with charge transfer. So the ratio of these two charged resistances is described using a dimensionless quantity called the Wagner number. So this is just an indicator of charge transfer resistance to ohmic resistance. And this is just implementation of these formula into the formula for Wagner number. So where is this become important? Where in which situation? Supposing you have a situation wherein anode and cathode distances are different in different parts of the system. It is a single electrochemical unit, but the distance between anode and cathode is varies. So where is this important? For example, supposing you have a nozzle of a spacecraft, which is a large device, and you are electrodepositing a particular material, let's say a good thermal conductor onto a space nozzle. This really happens when it comes to applications involved with space crafts and so on. So in that case, the metal is taken out of the anode and then deposited into the cathode. And because of the complicated geometry, the distance between the anode and cathode might differ. So with respect to this process, there are three resistances. There is a resistance associated with the electron transfer at the anode electrolyte interface. There's a resistance associated with the electron transfer at the cathode electrolyte interface, and there is a resistance with respect to an ohmic drop. So in this case, the resistance associated with the ohmic drop, this resistance is much larger than the resistance associated with the electron transfer at the anode electrolyte interface or the cathode electrolyte interface. As opposed to that, you can consider another case wherein the resistance associated with the anode electron transfer at the anode electrolyte interface, that is Ra and Rc, are larger than R omega. So the question we are trying to ask is, in which case would you have uniform electrodeposition? Because R omega is more than Ra and Rc, in this case, the R omega would vary in this part as well as this part, okay? Because R omega is dependent on L, as L varies here and here, or in all regions. The R omega, the value of R omega is different at different parts. Therefore, the potential drop associated with the ohmic drop is also different. Therefore, the electrodeposition characteristic across the cathode will also differ. In this case, because of the non-uniformity in ohmic drop across the electrochemical cell, you would also have non-uniform electrodeposition. Whereas in this case, even though R omega is different in different parts of the electrochemical cell, but R omega is not the dominating factor. So you would have Ra and Rc controlling your electrodeposition, and that doesn't significantly vary across your electrochemical cell. Therefore, even in this case, when L varies and R omega varies, you may still have uniform electrodeposition. So this is the way of thinking. So the question we typically tend to ask is, as a function of Wagner number, okay, how does electrodeposition uniformity gets modified? This is the kind of question you try to ask, okay? So here in this case, electrodeposition is indicative of current distribution at the cathode. So the question you ask is, how is the current distribution of the cathode gets affected as you modify Wagner number, going from low Wagner number to high Wagner number. So in this case, certain analytical results can be obtained if the current characteristic as with respect to potential is represented using linear kinetics. Okay, so this is one approximation. There are, see, with the fundamental phenomenological equation for describing I versus V is the Butler-Warmer equation, electrochemical kinetics. So that Butler-Warmer kinetics can be simplified under two limits. One is the linear kinetics, another is the Tafel kinetics. So typically, we use linear kinetics, that is under very low overpotential. And this formula under linear kinetics is represented using this formula. So in the next lecture, we will look at the ordinary differential equation for describing the current distribution. We'll look at that topic in the next lecture. Thank you.